So for reinforced concrete columns, there's something here that we call interaction diagram. Interaction diagram is going to be that relationship for a given column, which means now the column size, you know it. You have the width and then you have the length of it, cross section of it. And you have the reinforcing bars. And you have the concrete strength. And then you have your yield strength for the rebars. And for that specific column, you're going to be developing this relationship between the axial capacity and the moment capacity, which means the flexure capacity. You're going to jump here to slide number 23, just to show you here how it's going to look like. This is going to be one of these interaction diagrams. So I'm going to just take in this one of these lines, one of these curves. Try to understand what we're going to be trying to do here. On the x-axis is going to be the axial load. Don't worry about the designation that you're looking here at. Just consider this to be VPN. This is going to be the tension and axial force. And on the y-axis is going to be something here that's called Kn, which is Pn divided by this. So one axis here is going to be for the flexure capacity, which means x-axis, and the y-axis is going to be for the axial capacity. Let me go back here one slide just to show you another interaction diagram. And this is actually, I was able to get this out of a software after I run it for a given column. On the x-axis is going to be Vman. On the y-axis is going to be Vpn, which means axial capacity. The positive values here means compression. So let me write this down here, compression. And the negative value here indicates tension. This is something that we are not used to, because we are used to, when we see here, axial compression is going to be negative and axial tension is going to be positive. But in this slide set, we're going to be using it differently, because usually columns are exposed to axial loads. And to make it easier when it comes to our analysis, the compression is going to be positive and the tension is going to be negative. And this Vman, direction of it is not going to be that critical, because most likely a column is going to be like this section. So if someone's going to call this moment to be positive, which means causing compression on the top, someone else can just look from the other side saying, no, I can have it to be compression on the bottom, and you can call it positive. So direction here is not going to be that critical for us at this point. And we're going to have only positive moment, which means moment is going to be only in one direction. So I'm trying more to understand what's happening here, what is going on here. So I'm going to say here, in the top, I have a straight line. So this value here is going to be Vpn. If the moment equal to 0, this is going to be our column with axial load equation that we're used to. The Vpn equals, and you know the rest of it. Just going to put it there for quick, so that we don't forget what we're talking about. I'm talking about this equation, the very simple equation. This equation is taken from slide set number 9, and this is page number 8. This is going to be the very simple equation that we're used to for only axial compression. So when you have this axial compression, it means that you're going to have 0 moment acting on the column. So if you like, I'm going to come here and say, here is the y-axis. At this point here, the moment equal to 0. And this is going to be Vpn value that I just did based on this equation. So if you like to use this equation here, it's going to give you a point on the interaction diagram, which is going to be this point here. So what's important about this point? At this point, what happened? I'm going to put it here. I'm going to say M sub U is going to be equal to 0, which means no moment at all. It's going to be only Vpn. So it's going to be only Vp sub N, based on the equation that we're used to use. It's going to be this point. So okay. How about this point here at the bottom? This point is going to be the tension point, which means the tensile strength, if you like, with no moment at all. And if you like, I can give you an equation to find out this point here and the axial tension in this case, which means phi Tn is going to be equal to As times Fy. It's going to be that simple. So I was going to say, how about the concrete? I'm going to say this is here an axial tension. There is no moment at all, and there is no compression on the section. Entire concrete section is going to be cracked, and therefore the only tension member that's going to be acting with me or component is going to be the steel rebars. So if you have the total cross-section area of all the vertical reinforcing bars multiplied by F sub y, it's going to give you your phi Tn, and then of course you need to say I'm going to multiply it here by phi, and phi in this case I'm going to say phi is going to be equal to 0.9. Why? Because this is now tension control. All the steel is going to be in tension. So I simply can say phi Tn is going to be equal to phi times As times Fy. As, total cross-section area in the column, and F sub y, yield strength. Any moment now on the column, I'm going to say no moment at all. This is very good. So, okay. Any other significant points? So I'm going to say, here's point number 1, point number 2. I'd like to think here about this point. For me, I feel it's going to be kind of important. Now, what signifies this point? I'd like to hear from you guys. I'm going to go to Alan, please, if you can help me in this. Alan?
Yes.
Yes, please. Can you help me with this point? Can you tell me what's the significance of this point? What's happening here?
At that point, the phi n is 0.
So there's no moment?
Oh no, there is moment, but there's no
Axial load.
actual load there.
So what happens in this case? This is gonna be like what? Like a beam? Is this like a beam section? If I give you here any concrete section with some reinforcing bars and just put moment no axial load, would you call this like a beam section? Right?
Yeah, like a beam.
Yeah, it's gonna be like a beam. Why? Because there's no axial load, and mostly we call the beam because it doesn't have any axial load, but the column is gonna have an axial load. So if you take this given column section and do analysis, thank you, Alan, you're good, thank you. So if you take this column section here, any column section like this one that we developed this diagram for it, and you just find out phi mn as if there's no axial load, this is not now a column, you're going to be getting this point. So this point here is going to be phi mn, I'm going to say as a beam section. Now, I guess someone is going to say, do we have here compression reinforcing in this case? When you do a beam section, you can say yes. And if this section had been a T section, it means this is going to be the interaction diagram, and this is going to be phi mn for the T section, including the compression reinforcement. So this is going to be the final point that you get if you're doing it as a beam design. So I guess we're good with this point, good with this point, good with this point. I'm wondering what is happening here in this area here, because this area here depends on the analysis that you do and how accurate you're going to have in terms of your analysis, right? So I'm going to say in here, I'm going to have a point coming this way and a point coming this way, right? I'm just trying to simplify it, right? Say it's about like here, okay? Maybe something like this. What's important about this point here? I'm going to say at this point here, something is going to happen, because when you look here at this diagram and look at this section, say, okay, let me go here and let me compare this two values with these two values. So I'm going to say, what two values? I'm talking about phi mn with phi pn, right? I'm going to say this is here phi pn and phi mn. I would like to compare this point. I'm going to call this point point 1. I'm going to call this point here, this is going to be point 2. This is going to be here point 2. Now look what happened. Between point 1 and 2, you're adding some axial load, right? And what happened to the flexure capacity is going up. Still not clear. What do you mean? What's going on? I'm not clear yet on the meaning of this interaction diagram. This interaction diagram includes all the combinations of axial loads and moment, strength for that given column. Meaning, if you have any combinations of an axial load and moment value, and you put them to this column, and let's say, for example, your moment, applied moment on this column was equal to 300, and applied axial load is equal to 900. So I'm going to say my point is going to be here. Are you guys with me? It's going to be within this envelope. It means this column is safe under this given combination. What's the combination now? I'm going to say here a moment demand of 300 and an axial demand of 900. So this combination, my column is okay. Why? Because this point here is falling within this envelope. So I'm going to say, how about if I have phi man of 400, like in here, and the assumed axial demand is going to be 1500. So, okay, now I have a demand of 400 moment, and axial capacity is going to be 1500. So the point is going to be here. Is this good? Can my column support this combination of this moment and axial demand on it? You can say no. Why? Because it's going to be outside of this envelope. So any combination of an axial demand and moment demand, any combination, if this combination here falls within or right on this envelope or diagram, you're good. Your column is good. Once it goes out of this envelope, your column is not good. Your column cannot support any point here on the outside. Again, if the combination falls within this envelope or on this envelope, it's going to be right there on this line, your column is going to be okay. It's going to be able to support this load. Now, based on this understanding, I'd like you to review this significant point. So these points here, the first one is going to be the PPN when you have no axial load. And this is exactly the one that we have used when we use this equation. If you remember this equation means what? It means the capacity of the column when the column is exposed to axial load only. No moment. Look at this. Moment here is going to be equal to 0. You say, how about this point here? What happened at this point? Like what Alan answered me. At this point, axial load is going to be equal to 0. And this point here is going to be equal to phi man, as if I'm handling this column section as a beam. So now understand this point, understand that point. This point of a kind of a new point to us. Let's give you the capacity of this column section exposed only to tension force. Because look at this. This here is going to be the zero moment, zero axial load. Therefore, it's going to be the tension side, and this is going to be the compression side. And this tensile strength of this column section, no moment at all in this point, is going to be equal to AS times Fy times phi factor 0.9. Great. Now I am good about the 3 points. Now I'm trying to compare here between point 1 and point 2. What happened along this curve? You're adding here an axial strength, right? Or an axial demand. You add some axial force on the column. What happens to the capacity? Does it go up or it goes down?
It's going up.
It's going up. It's kind of weird because I had this feeling when I have a column, I'm going to start here to add an axial load to it, that the flexure capacity is going to drop down because you start to load it with some forces. So for example, here's a column, you start to add axial load. What happened to the flexure capacity? I would think it needs to drop down because you start to add some loads to it. But this is kind of weird because what's happening, the axial capacity is just going up for both the axial load and for both the flexure capacity. Which means if I have a column that's supporting about 150 kips, this column, specifically this column here, And this column here supports 150 kips. I'm going to be adding here additional 150 kips to have a total of 300 kips. Instead of having a capacity of, let's say, 420 or so, now it's going to become 520 kip foot. So the strength, the flexural strength is going up. But when you look at these 2 points, so I'd like here to look at these 2 points, right? So I'm going to say this point here and this point here. Look on the top. Now, this point here, you have an axial demand, right? Of how much? 1,200 kips. Let's say that you put here 1,200 kips on the column, right? Now, all of a sudden here, you start to reduce the force from the column. You start to reduce it from 1,200 to 900 kips. Why 900 and 1,200? Because it's going to be the axial load demand. Now the axial load demand dropped down to 900. What happened to the flexural capacity? Did it go up or it goes down? Now it moved from 400 to 500, which means the flexural capacity here, it went up. So something here about the slope of this line and the slope of this line. The slope of this line, when you start to add here more axial force, what happened? The flexural capacity increases. But the slope here, when you start to add here more axial load, like you're at 900, you start to add here to 1,200, what happened to the strength? Moment capacity starts to drop down from 500 to 400. Do you guys see what I'm talking about?
Yes. Professor, one quick question. So I see that there's tension at the bottom, and you're mentioning the axial load and such. So when does that happen, that tension part? Is it just when I'm kind of confused? I'm trying to like visualize how everything is working and
Just think about the column.
Mhm.
A column. And this column is supporting a floor. And this column is not really a column, it's a hanger.
Mm-hmm.
It doesn't go all the way to the ground. So this column is exposed to tension force. Make sense? Or no?
I think I got it.
No? Not good?
I'm currently looking up images on my side.
Hold on. How about this slide here?
Oh, okay. Mm-hmm.
This column exposed to what? To compression. This
Mhm.
column compression, this column compression, because the load is going to be going downwards. How about this column here, exposed to what?
Tension.
Tension. So how do you figure out the strength of this column? Well, what you need to do, because the entire section here is exposed to tension, right? So what you need to do is say phi Tn, which means the strength and tension of this column is going to be equal to the total cross-section area of the vertical rebar multiplied by F sub y multiplied by phi factor of 0.9.
Mm-hmm. Okay.
One of the questions that you're going to say, why 0.9? I'm going to say, hold on, you're not that far. What happened when you have tensile strain? When you're right there? It's going to be all tension controlled, correct? You're going to have lots of strains in the rebars, which means your phi factor is going to be 0.9. So, okay, I guess now I'm clear on where the column is going to be in tension and where the column is going to be in compression. It's just an example. So coming back to here, no problem. Coming back to here, what I'm trying to say here, we're going to have this interaction diagram for each concrete section. And this is going to be the most detailed analysis that you can do to a concrete section when you do this interaction diagram. Interaction diagram is going to be a relationship between the axial load and between the friction, the moment. When you have M and P in the same time on a section. And this interaction diagram is going to have certain significant points. These points, the first one, like what we were talking about, when you have a column with no moment at all applied to it. So here I have no moment. Why? Because you're talking about this point, when the moment equal to 0. This point here is going to be representing the equation that we used to use. for short columns. This equation here. Okay, understand this. How about the bottom equation here? I'm going to say now this gives me tension. And the equation for tension, phi Tn, now this going to be phi. I need to put it as F. Is going to be equal to the cross-section area of the rebars, multiplied by F sub y, multiplied by phi factor of 0.9. So I'm good about these 2 points. Any questions from anyone about these 2 points? Does anyone have a question? Why are we doing this? Or what is that interaction diagram that you're talking about? Or I'm not really clear on what you're talking about. And let's just start from the beginning.
I have a question. So when
Yeah.
I looked at the diagram, I saw 4 lines.
What?
Sorry, three lines. So the one with the positive slope, yeah, that one.
This one?
Yeah, and then the one with no slope, the horizontal one, and then
And then a
this,
horizontal one.
and then, yeah, and then the other one with a negative slope. What's causing these lines?
Absolutely. We're going to be talking in details why this is flat, why this is going down, why this is going up. We'll talk about this. Absolutely. We're going to discuss it in details. But to understand this, right, I need first to go to this significant points, if you like to call them this way. Some important points here that I need to address first before we continue. Some of them, we know about it already. The 2 famous points that you guys know about is going to be this point here, when you have no moment at all and you have just an axial load. You can say this is going to be our equation, right? And with this equation, you should be able to figure this out. So this is going to be the simplest one that we know about. The second one is the one that we started with. This is going to be phi Mn for a beam. To remind you with this, just going to open one of the slides. So we say, okay, let's look at this here. You remember this equation? This equation phi Mn is going to be equal to As times Fy d minus A over 2. The very simple equation. And then later on, we'll make it a little complex. We start to add compression reinforcing. And then we start to say, now I'm going to have here a T section and so forth. But no axial load, right? In this equation, this is what we started with. There is no axial load. And actually, this is the equation that we're talking about. And this gave you the point that we're talking about. In here, no axial load, and you just have moment. So these 2 points are the 2 points that we solved for already in our analysis this semester. Does this make sense to you guys? I just want to be sure that everybody here understands the significance of these 2 points. And you're aware that we determined these 2 points already. In terms of, we know how to figure them out. We know when I just have an axial load and no moment, how would I get to this point? And you guys know when I have no axial load, this is going to be phi Mn, like any section that we have discussed. Are you good about these 2 points or no? Not yet.
No, can you explain it a little bit more, Professor?
Okay. Tim, you're just in? Tim, are you there?
Yes, I'm here. My internet dropped out.
Okay, Tim. Okay. Let me do this again. And please stay focused with me, if you don't mind. At the beginning of this semester, we started by this cracked section and uncracked section, and then we do this section here. We start to say reinforcing, and then we are able to find at the end something that you call here flexure strength, phi Mn. So everybody follow me? Yes? I'd like to hear from everybody, please. Otherwise, I feel that you guys are either away from your computer, you're not there. I'm just talking here to myself.
Yeah, we're good.
Yes,
Yeah, good.
you're not by yourself.
So find out phi Mn, we went through steps. We did it first when I have just a rectangular section, and the section was so simple, and we say no compression reinforcing would be considered. That was the first step. Second step, we start to say, what happened if I have a T-section? You guys remember T-sections?
Yeah, I remember that.
Yes.
Yeah. Second step, T-section. Said, okay, here's a T-section and just some tension reinforcing. Third step, we start to consider the compression reinforcing that we have already there, but usually we are ignoring them. So that was all about the T-sections, right? And then we start to make it more complex. We start to put here the compression reinforcing in our analysis. We start to put this, right? And if you really want to make it very complex, you need to put the T-section with the compression reinforcing at the same time, and then you do your analysis to find what? Find out PMN. I'm gonna come back here to this. I'm gonna say that was the ultimate goal that you'd like to find out. Is gonna be PMN, the flexure strength. Everybody following? Yes?
Yeah.
Yes.
All
Yes.
right,
yes, yes.
great. All right, good. Is it good? Now, after we were done with the beam design, we started the column design, correct? And then we start to use this equation. We say this equation is simple and it considers small eccentricity. You remember this small eccentricity thing when I discussed it?
Mhm.
And I said, this equation here does not consider what? Any moment acting on the column or the concrete section, correct? No moment at all. So now I have two things that I have learned. I learned how to find out PMN for a beam and PPN for a column with no moment. So at the beginning, when I said PMN for a beam, I said that no axial load demand on it at all. There is no axial load acting on the beam. When I start to work here on the column, I said no moment here acting on the column. It's gonna be just pure axial load. Following? Yes?
Yeah.
Yes.
Yeah.
Alfred,
Yes,
are you
yes.
there?
Yes.
All right. Now I'm looking here at this interaction diagram. I said, now what happened to the direction diagram? Guess say this interaction diagram, it is a relationship that shows all combinations here of axial load and moment acting on this column or this concrete section. So now I'm gonna have a concrete section that has an axial load and a moment acting at the same time on it. Now I need to do the analysis for it. You see the direction I'm going? So at the beginning, I have no beam. I have just a beam, no axial load, just moment. On the other hand, I have a column, no moment, only axial load. Now, all of a sudden, I'm going to be bringing here one concrete section. I'm going to say now this concrete section is going to be supporting axial load and moment in the same time. Okay. Again, this interaction diagram is going to include all combinations of the VPN and VMN. All the combinations.
So a quick question. So the FMN, that's so the F represents just phi, correct?
Yes.
Okay, just making sure. For my notes.
Professor,
Yes.
so you said that the column is no moment, but there's axial load, and then the beam, there is no axial load, but there's a moment.
This is what we studied so far, right?
Mhm.
This is what you know about. This is what we have been talking about.
Yeah,
Okay.
just
So
confirm it from the diagram, because so we
okay.
already know that's the
How
beam.
about here? How about here? What is this? You remember this light set, rectangular section? What happened here? Was there any axial load in our work, in our business?
No,
Okay, good. All right. How about in this column equation? Was there any axial load? This column equation here, was there any moment acting on the column?
no moment was acting on them.
Okay, there's nothing. Okay, good. So this is the only two cases we studied. A concrete section with only moment and another concrete section with only axial load. Are we good, everyone? Yes?
Yes.
Good.
Yeah.
All right, great. Now I'd like to combine this axial load and this moment on the same concrete section. And I decided to call it a column. This concrete section, I decided to call it a column because most likely all columns in all buildings, they're getting exposed to some axial load and some moment in the same time. There is no column with pure axial load like the way we covered it here, right? Like in here, it doesn't happen. And there is no beam with only moment demand on it. There should be a little bit of an axial load, but we just ignore it, right? And this is what we used to do in the past. Now I'd like to change this fact here, or this information that you know about, and tell you that any concrete section is going to be exposed to some axial load and some moment in the same time. Okay. I said, what is this interaction diagram? This interaction diagram is going to be the path over which you have these combinations of axial load and moment on that concrete section. And this here represents the capacity line or the capacity point. And if the combination of this axial load and moment demand is going to be happening within this envelope, it means your column is safe to support, or your concrete section is safe to support this combination. If the combination here is going to be falling out of this envelope, what does it mean? It means your section here is unable to support this combination of an axial load and moment. And I said, let me give you here an example. Okay, I have an axial load of 1500 kips and a moment demand of 400 kips. You think your column is going to be able to support it? I said, what are you talking about? Say it again. I said, axial load 1500 kips. This is going to be this line. And moment demand acting in the column at the same time of 400. I said, well, the combination is going to be out of this envelope. Your column cannot support this combination. I said, okay, good, thank you. Now I understand. Let me give you another combination. I'm going to say I have a combination that says I have a moment demand of 200 kip foot. Here is 200. And an axial load of 600 kips. Is your column okay with it? You see, yes, look at this. The point is going to be right at the center of the circle here, right? So for this combination of 200 kip foot and 600 kips, your column is okay because this point or this combination here falls within the envelope. So as long as the combination falls within the envelope or on this perimeter of this envelope, right, you should be fine. Once this combination is going to be falling out of this envelope, your column is not good anymore to support this moment and axial load. Are we good? Yes?
Yes.
I'd like to hear from everybody, please. Yeah, from everybody.
Yes, we're good.
Yes.
Okay.
Yes, sir.
So now I'd like to draw this for a given concrete section. So I need to know the important points. Otherwise, my job is going to be like up in the air. I don't know exactly what's happening. To simplify it, I'm going to say this is going to be composed of a few lines. And how many lines? I'm going to say it's going to be one straight line here, one sloping line coming here like this, another sloping line is going to be coming this way. So how many lines? You're going to have 1, 2, 3 lines. How many significant points? Yes, say significant points. Here is 1, here is 2, here is 3, here is 4, here is 5. Do you guys agree?
Yes.
You need to have these 5 points to be able to do interaction diagram for a given concrete section. And here I'm going to be calling it a column. So I don't someone here to think columns do not support moment, they support only axial load. I'm going to say, no, this is what we started with, just to give you a concrete section exposed to only axial load, and then we'll start to call it a column. So I don't want you to think that columns support only axial load. They all support axial load and some moment. And also beams. Beams, it's going to be a false understanding if I'm going to tell you here, beam supports only moment, because all beams support some moment and some axial load. But most likely, the moment is going to be the big factor. In columns, the big factor is going to be the axial load, and the moment is going to be the small factor. Okay. 5 points that I need to be able to figure out if I'd like to do this interaction diagram. The first point here is going to happen when you have only axial load acting on the column, and they have what? Only axial load and no moment. I said, yeah, I understand this one. I have done it before. Where is this point and what's the equation for it? I'm going to say this is going to be the equation for this point. only when I have an axial compression, right? And no moment acting on it. Say, how about this moment here? What happened at this point? At this point, I have no axial load, and I have only moment acting in the section. I'm going to say like what? Let's say it's going to be something similar to this that we started with. This female, the very simple equation. And then we made it, after the fact, we start to make it more complex. So we make it more complex when we start to do a T-section, compression reinforcing, and the whole 9 yards. Okay.
Professor,
Yes.
at that particular point, is
Yeah.
that at that point is the equation m sub n, that one's that equation is applicable at only this point, is that correct?
Yes, this is correct.
Okay.
Why? Because at this point here, I did not introduce any axial load to the picture, right?
Yes.
So
that's
now I'm done with 2 points that we know of. I'm going to introduce here a new point here. I'm going to say, how about this point here? What happened? We're going to have only tension force and no moment, correct? Moment here equal to 0, right? And only tension force. The capacity in this case is going to be equal to phi Tm. And you need to understand that this F, right? If you like to change the font, which I'm unable to make it here in Adobe, is going to be the phi factor. So I'm going to say here, the strength of this point, or this point, the coordinate of it, is going to be 0 in the x direction, and for the y direction, it's going to be negative. Why? Because we are used to, when we are working with column concrete sections, when you have an axial load coming to it as in compression, we consider it to be positive value. So I said, okay. So nothing is wrong here. When you see here positive value says compression, it's okay. This is fine. This should be fine. Now, in this tension side, the strength is going to be equal to AS times Fy multiplied by the phi factor, which is 0.9 phi factor. So now how many points do I know of? 3 points. I still have 2 points, this point and this point here. What happened here at this point? If you notice here, the flexure strength is growing up with the same axial load, right? In other words, the strength when it comes to this concrete section and axial load, it is the same even though that you start here to add some moment to it, which is kind of weird. I mean, it doesn't make any sense. How come you have the same strength when it comes to flexure capacity, right? You have the same strength here for this axial load capacity, even though that you start here to add some demand as a flexure to it. Doesn't make sense. Something's wrong. It doesn't make sense. Does it make sense to any one of you guys? What's happening here? Why this is like a straight line?
Isn't that where the concrete is working and then the steel begins to take the load?
Okay, let me clarify this to you. Let's just here jump a little bit to the second, or this here interaction diagram. I'm gonna say, where is this flat part? I don't see it, correct? Do you see this flat part on the top? No.
Yep.
Where is this flat part on the top? As if I have a feeling that this line used to be like this, and someone decided here just to cut it off. Someone says, no, just go here to this equation, right? Which equation? I'm gonna say, this equation here. You remember this equation? And someone says, let's just stop the diagram up to this point. I said, okay, good. What is the reason? The reason is because they'd like to consider some flexure demand that acts on the same time on any given column. Because they say, you know what? There is no column with any moment demand of 0. It doesn't happen. Which means it doesn't happen that you're going to see a column here with 0 moment. So this is why we cannot just let you use this value here. We're going to drop it down to this value. And how much is this drop, you think? This drop is equal to, how much here? Is equal to 20%. Why 20%? This drop here is to take care of the small eccentricity effect. So if you'd like to ignore here the small eccentricity effect, you should have used this factor of 1. So this factor actually, or this value here, is going to be 80% of this value if you would have extended this curve all the way to here. So why do we do this? It's kind of safety, because we know usually columns is going to be supporting a little bit of some moment, but we just ignore it. We don't We don't do anything about it. We can just ignore it. There is no column at all without some moment acting on it, right? So I guess we understand this factor here, that this now here is going to be 0.8. And how much is this? I'm going to say, I'm going to come back to you on this. I'm going to tell you exactly how much is the moment right here to come up with the coordinates of this point. So, okay, good. How about this point here? What happened here? What happened here, I used to add some axial load and the flexure strength was just going up. And here in this line here, what I'm doing here, I'm start here to add axial load and look what happened. The flexure capacity is dropping down. So I'm trying here to understand what is the difference between this curve, the slope, and this curve and what happened here. Just, you know, at this point, we understand that at any point in here along this diagram, the strain in the concrete is going to be equal to 0.03. You guys know this, right? EC, what is EC? What does this E means? The strain, which is epsilon, C is going to be equal to 0.003. You guys know this, right?
Yes.
This way we consider the concrete to be failing when the concrete strain approaches 0.03. But at this point, what happened? The strain in the steel is going to be exactly equal to the yield point. It's going to be equal to that. We call this the balance point. So what happened at the balance point? At the balance point, the concrete is going to be exposed to a maximum strain of 0.03, and the tension steel is going to be exposed to the yield strain. It's going to be right at the yield strain. It doesn't happen at all points, because usually you're going to have either one of the two. The strain in the tension steel is going to be either above the yield point or below the yield point. We understand that, and we have done examples on this. Am I correct?
Mhm.
You guys remember this?
Yeah.
Okay. So either you're going to have here compression control or tension control. Now, where do you think the compression control is going to happen? Is it going to happen beyond this point here in this direction, or is it going to be happening here? I'm going to say, look at this. This is going to be more like compression, like column, like pure column with axial load, just pure axial load, right? So this side here is going to be the compression control, and this is going to be the tension control side. And this is going to be the point between them. We call this the balance point, if you like. Someone's going to say, but we have this transition zone. When the strain is equal to 0.03, if you remember 0.02 to 0.05, correct? You say, okay, not very clear on this. I'm going to take you back here to this guy, to this chart. When the strain is going to be equal to the yield strain, what happened? We call this compression control, and then we have transition, and then we have tension control. So in here, what happened? Where is the balance point? Balance point is going to be right here. So this balance point, which means right here, right at this point here, the strain is going to be right there. The strain in the tension steel is going to be right there. Then when you go down a little bit, you're going to be in the transition zone. And then after this, you're going to be in the tension control. And this side is going to be compression control. When you do the analysis, it depends on the reinforcing configuration and the strain and the stresses and the whole thing. Sometimes this point would become right here. It's going to be becoming a little bit above this point. Let's say about right here. Okay. So the location of this point is kind of moving a little bit, depends on the section and the analysis and the whole thing. All right, now let's start from the beginning and see what is this about. So again, interaction diagram. Now we have an idea about the interaction diagram. It's going to be a relationship between the capacity in axial load and capacitive flexure strength. And we can do this with a diagram. We can develop our R diagram from the analysis if you like. Most likely you're going to have a software to do it with it. You know, the software is so simple, you run it quick. You just put the column parameters, dimensions, strength, reinforcing bars. It's going to develop this diagram for you, like the one I just showed you. So here's a column, like in the 3D. And the column usually is going to be exposed to an axial compression force. It's going to have some eccentricity. So this E indicates eccentricity. When you look here from the side of the column, you see here that you are going to be rotating the moment about an axis that runs perpendicular to the screen, which means this axis, correct? This moment is rotating about this axis. This means this P sub u, which means the demand, and this E means at the end that you're going to have a P sub u axial load right in the middle of the column. We're going to call this concentric force. Concentric means right in the middle of the column, no eccentricity. And we're going to have a moment, and this moment equals to P sub u times E. This is going to be the moment applied on the column. So in this case,
could you repeat that one more time? So piece of view is directly in the center of eccentricity.
okay, let's start all over again. You understand this diagram, right? This gave you like a 3D for the column exposed to some axial load. But this axial load is not really in the center. I'm going to call it here eccentric force. What is eccentric force? It's a force that's not acting at the center of the column. It's going to be shifted a little bit. Shifted with a distance that we call eccentricity, E. E is going to be like a dimension. It's going to be like 10 inches, 6 inches. It's going to be some number there. It's going to be assigned to you. Now, it means that this column here, when you look from the side, that this column here is causing moment about this axis. So this axis now becomes perpendicular to the screen. So you're going to have this axial load with some eccentricity. If you like to relocate this axial load and put it right in the middle, you're going to have additional effect of P sub u times E. And I guess you guys studied this in statics, or maybe structural analysis 1. Anyone remembers this method or this theory? Castigliano theory? Yes?
We didn't do Castigliano's for the deflection when we took structural analysis. We did virtual work for the conjugate beam.
All right. So what it means here, that I can replace this system here, P sub u, and this E with some eccentricity. I can say that this system here is equivalent to this system, to these two forces. So when you have P sub u at eccentricity of E, it's going to be the same as if you have P sub u. It's going to be concentric force with some moment. And this moment is going to be equal to P sub u times E. It's going to be P times E. So this system here, forces, is equivalent to this system of forces.
Got it. Thank you.
All right. Now, what is the source of this? It's interesting. Why don't we have all the forces coming right in the middle of the column? I'm going to show you here the sources. One of the sources, I'm going to start with this guy here. I'm going to say this is like in a parking structure. You have reinforced concrete parking structure, and then you have this bracket, or sometimes we call it corbel, concrete corbel. And here's the beam. Here's the support for the beam, and the force is coming like this. Now, where is the center of the column? I'm going to say center of the column is going to be right here, right? Because I'm going to be interested in working on this column section, which is right here, right? So I have this amount of eccentricity. Now I understand the source of eccentricity. In precast construction, the bearing for the support of the beam is going to be on a bracket. It's going to be offset from the center of the column. Now it makes sense because let me take you back here. I understand now where is this E coming from, right? Because of this reason. Say, how about here? What happened here? What happened in this location? That some cases, on one side of the column, you're going to have that you have here dead load on live load. On the other side, you may have only dead load. This is something that you never consider when you do column analysis. You're just trying to maximize the load on the column. So what's going to happen in this case, this beam wants to bend down a little bit more than this. And the column in this case is going to be exposed to some moment, and the moment is going to be rotating the column this way. Look what happened. Also, when you have simply supported structure, you think that this is really a pin, like in this case. This is here a pin support, right? This completely simply supported. This is how you consider it. But because the way we build it, we actually develop some fixity here at this location, at the end of the beam. This is not really pin. We consider it to be pin, but in reality, there's not like pure pin. Pure pain is going to happen with some friction. In steel construction, it's going to be very special. But in concrete, you're going to have the rebars and the concrete and the continuity. And this one here is going to have certain moment capacity here at the end. So you're going to see here some moment is transferred from the beam to the column. So actually, this column exposed to some moment. So you're going to say, now I understand that any column on Earth, it has to be exposed to some moment with the axial load. You cannot just have a column with no moment acting on it. It will never happen. You just give a combination of lots of axial load and a little bit of moment. Like in beams, what happened in beams? You're going to have lots of moment and a little bit of axial force acting on it. We can have an example here. It says, find the design axial load VPN for the tight column for the following conditions. What is the first condition? It says here, small eccentricity. Yes, say, what does it mean by small eccentricity? It says when E, the eccentricity, is going to be ranging from 0 to 0.1 of h. I said, okay, now this is going to be definition for a small eccentricity. So in the past, when I did this column equation to you, right? I said that this 0.8 here is going to be for the small eccentricity effect to cover it. Now, we didn't question the meaning of the small eccentricity. Now, this is the time to understand what does mean by small eccentricity. Small eccentricity, when E is going to be equal to maximum of 10% of the h. What is the h in this case? I'm going to go back here. Where's the eccentricity? Oh, it means if you take the moment divided by P, it's going to be the amount of eccentricity E. And your E max for a small eccentricity is going to be equal to 10% of h. Now, which one do you think is h? Is it going to be this length? Or is it going to be this width? Which one is h for you, for the column?
I would have to guess it's kind of this front area.
What do you mean? Is it going to be this length or this length? What is h?
I want to say the horizontal.
Okay, let's look at here. Yes, okay, let's look at this section. It says a column cross section shown below. Assume short column bending about y axis. What does it mean? Here's the y axis. So the moment is coming this way. The moment is going to be causing here, let's say, some compression, and here's going to be causing some tension. So this is going to be h. So your h here is going to be equal to 20 inches. I'm going to say here h equals 20 inches. Total depth of the column or the section is going to be equal here to 20 inches. How about this one? You can see now this is B. This is a B I'm used to work with. B is equal to 14 inch. Very good now. We understand the definition of the depth in this case. Why? Because the moment is going to be coming this way.
Mm-hmm.
Because bending is about y axis. It means for the small eccentricity, based on this definition here, that E is going to be ranging. I'm going to say this is going to be only for the small eccentricity, right? It means E is going to be ranging from 0 to 10% of h. How much is 10% of h? 2 inches. Right? As long as the eccentricity is going to be equal to a maximum of 2 inches, which means the axial load, let's say the axial load is going to be here like a circle, right? It's going to be like this. Am I correct? Because axial load is going to be perpendicular to the screen. And I'm going to say this is going to be the distance from here to there. And this is going to be your E, the eccentricity. I'm going to put it here. I'm going to say here's eccentricity. Right? As long as this eccentricity is equal to 2 inches, the axial load capacity of the column can be determined using this equation. Are you guys following me or no?
Mm-hmm.
It's good?
Yes, we're good.
Yeah.
All right, great. So now I have the definition of eccentricity. E, when it comes to small eccentricity, is going to be maximum of 10% of H, maximum of 2 inches. All right, so this is going to be item A. Item B, they are also looking for this VPN. When you have E equals, look at this, 5 inches. Okay, yeah, I guess we're going to be working on this. You see, C, which is the last one, it says at the balanced strain condition. What is the balanced strain condition? When the tensile strain is going to be equal to 0.02, which means the tensile strain here, or the steel exposed to tension, is going to be right at the yield point, and the compression concrete on the other side is going to be right at 0.03. This is going to be the balance point. And then they continue here, they say strength of the concrete is going to be 4,000, for the yield is going to be 60,000. Give you some dimensions here, 14 by 20, and then they put here 6, number 9. 3 in tension, room compression, and 3 is going to be in tension. So, okay, good. I understand. Now I have all the parameters I need. Now let's go here to solution. Item number A, when you have a small eccentricity, and how much is going to be VPN and VMN? Not very clear, but we'll see it. Here's the cross-section area. You have 14 by 20. Yeah, 14 by 20. And then you have here 6, number 9. AB here for 1 number 9. I'm going to say A sub B for 1 number 9 is how much? 1 square inches. Okay, so it's going to be 6 square inches total. For the small eccentricity, as we said, I should be able to use this equation. This is going to be the simple equation for axial compression capacity of a concrete section. We said here that we're going to have this 0.8. What is the 0.8 for? Say 0.8 for the small eccentricity thing. Yeah, okay, now we have this 0.8. And the phi factor is 0.65 for tight columns. Yes, this is going to be tight columns. I don't see here a spiral column in front of me, so I know that I'm going to be using this factor, 0.65 and 0.8 instead of 0.85 for a spiral column. So good. So what is that term for? I'm going to say this term represents the concrete strength, and this term represents the steel strength. Yeah, 6 times 60, 6 square inches times 60 f sub y. And here's going to be 0.85 times f prime c, the 4K psi, times AG minus 6. What is AG? Gross section area. Subtracting 6 square inches, the steel section area. How much is the strength in this case? I'm going to say this is going to be equal to 672 kips, ppm. I'm clear on this. This is exactly what we have done in the past. Now we need to understand what does mole by small eccentricity. Small eccentricity is going to happen when E equals 0.1 H, which means when E equals to how much?
2 inches.
2 inches. Very good. And at that point, how much is the moment is going to be? You see here, phi man is going to be equal to what? It's going to be equal to VPN. How much is VPN? 672
672
divided by
times.
2 divided by 12. What is this 2 divided by 12? It's going to be the amount of eccentricity. And here we go. It's written right there. The moment capacity now is going to be equal to the axial capacity multiplied by E. And E in this case, a maximum of 10% of H. This is going to be times 20% of H. 672 times 0.1 times 20 divided by 12. Just take here 10% of 20 is going to be 2 inches. You divide here by 12. It's going to be 112 foot. So as long as this column is exposed to a moment that ranges from 0 to 112, your axial load capacity equals 672 kips. Clear or no?
Yeah, Professor.
Let me write it down again. Yeah.
So then this value would change if instead of it being 20, it would be like something larger, 24 by 14, correct?
If the column size change?
Yes.
Yes, absolutely.
And it would just change by a factor based on relative to the.
You just do the analysis. I'm going to just leave
Okay.
it like this for now. So I'm saying here, as long as, look at this, as long as M sub U is equal to, or ranges from 0 to 112 kF/foot. Phi Pn equals how much? Does this make sense? The statement here does make sense? I'd like to hear from you guys. As long as here the moment demand goes between 0 to 112, what did I write here? 112 kF/foot, which means as long as the moment value applied on the column is going to be within 112 kF/foot, which means this small eccentricity flexure, the Pn, the axial capacity, is going to be equal to 672. So, okay, I'm trying to understand it more. So I'm going to say, why don't I just jump to some interaction diagram? I'm going to say, okay, let's go here to some interaction diagram. Just try to understand how this is going to work on it. So I'm going to be opening this slide set, which is the same as this. I'm going to be jumping here to this interaction diagram. This point here is how much is this strength, Ppn? You remember the value that we came up with?
The 672.
Yes. So how much is this? I'm going to say this here 672 kips. Good. And I guess now I understand this is straight line, right? Why do I have a straight line? Because it says here, you're going to have the same axial load capacity as long as the moment is going to be ranging from 0 all the way to how much? Based on this on the bottom, to 112. So how much is the moment here at this point? This is going to be 112.
12. Yeah.
So the moment here equals 112 kF/foot. So again, as long as the moment capacity ranges from 0 to 112 kF/foot, what happened? The axial load capacity remains 672 kips. Said very good. This is very good. Any questions on this? Understanding the minimum eccentricity, understanding this issue of the small eccentricity thing that we consider for when you use this equation. It's going to be based on 10% of eccentricity of the depth of the column. What does mean 10%? 10% means 0.1 times h, the depth of the column. Here's the depth of the column. This one you consider here 10% of it. 10% of 20 is going to be 2 inches. So up to an eccentricity of 10%, which means eccentricity here of 2 inches, your column should be fine to resist the same axial load. This is what you're talking about. Now, I guess if I may jump here to slide number 23. I actually give you this line. What are the points that I'm now able to find out? What did I finish so far? Let's say I was able to do this, right? And also I was able to do this. What's happening here? At this point, I have no flexure demand at all. I have just an axial capacity. How about this point? You can say this point here is going to be the small eccentricity point, and this moment, which means this x component on this diagram, this is going to be m sub u or phi man, if you like. This is going to be equal to how much? It's going to be equal to this axial capacity multiplied by 10% of the column depth. And how much is the column depth in our problem? It was only equals to 20 inches multiplied by 10% is equal to 2 inches. So, okay, good. Are we good? Can I move forward?
Yes.
All right, very good. So I'm done here with item A. So I guess I can put, oh, I don't have anything here for it, like a check mark. So we're done with this. Let's say this is good. Done with it. Second item, when the eccentricity equals 5 inches. You're gonna say, okay, let me move here to 5 inches. Item B. The eccentricity equals to 5 inches. One side is gonna be exposed to compression, the other side is gonna be exposed to some tension. Generally speaking, when you have a column with this small eccentricity, how would I know it's gonna be a small eccentricity? I understand it's gonna be kind of small. It's not really a large eccentricity because the distance from here to here is how much? Anyone recall the dimension of this column? How much is this? 1/2 of the column depth is how much?
10
I
inches.
said
7?
this is gonna be 10 inches. Where this is coming from? Where do I have it? You can say, okay, let's go back here.
That's when
Total column is 20 inches. So from here to there is gonna be how much? I'm gonna say here 10 inches. So 5 inches is gonna be like the quarter point of the column. So I'm expecting lots of compression is gonna happen on this rebars. Therefore, this rebars is gonna be yielding in compression. It's gonna be one of the assumptions. But this tension rebars, it's not gonna be re-yielding. I'm just expecting, and I guess my expectation is gonna come true. So I'm gonna say here, the strain in the compression steel, which means the epsilon S prime, is gonna be more than the yield strain. Therefore, I can just assume that the stress here in the steel is gonna be equal to F sub Y in the 3 rebars, the compression rebars. How about on this side? What's gonna happen? I don't think they're gonna be yielding. Therefore, I said that epsilon S, which means for the tension, is gonna be lower than the yield point. And therefore, the stress in the tension steel is gonna be lower than 60 psi, which is the yield point. So what are these assumptions based on? Expectation, experience, if you like. You can have any other assumption, and then you need to solve or do your analysis and prove it otherwise. Now, because I know what's gonna happen, I'm expecting this here, the compression reinforcing, to be yielding, and the tension bars not gonna be yielding. In section A here, we have the external applied force, P sub n. And then we have here the reinforcing bars. We're gonna have 3 rebars in compression, 3 rebars in tension. The depth to the tension rebars, I understand that it's gonna be 14 inch, 3 and 3. Therefore, I'm gonna have here 17 from the tension rebars to the top compression. In the top, the compression here, the compression strain is gonna be equal to 0.03. I'm expecting the strain here in the compression steel is gonna be beyond the yield point. Therefore, C2, which goes with the compression reinforcing, is gonna be equal to F sub Y times AS prime. You remember AS prime? Compression steel is gonna be 3 square inches, and AS is gonna be equal to 3 inches. So I'm expecting this to be yielding, and it's true, it's gonna happen. Now here's the strain in the tension rebars, and this is gonna be the strain in the compression, again, rebars. The depth of neutral axis is gonna be C. Compression C2 is gonna be for the compression the steel. Compression C1 is gonna be on the concrete. It's gonna be for a depth of 0.85 times C, because beta 1 equals to 0.85, and the amount of pressure acting on it is gonna be 0.85 A prime C. And here we're gonna have the tension the steel, and the tension the steel here, it's not gonna be equal to the yield point times AS, instead it's gonna be equal to FS times AS, because the steel is not yielding in tension. In the past, we used to say summation of the forces is gonna be equal to 0. So we used to say T is gonna be equal to C1 plus C2. Am I correct? Yes?
Yeah.
Okay. Here we have external force. So we cannot really say that T is gonna be equal to C1 plus C2. Instead, we're gonna say T minus C1 minus C2 is gonna be equal to P. Otherwise, this section is unbalanced. Because what's gonna happen to this force? It needs to be resisted internally. So you can say, for example, C1 plus C2 minus the tension force is gonna be equal to Pn. It's fine. You should be able to do it also this way. I guess I'm gonna stop here, and please go ahead and sign out. If you have any questions, I'm gonna open the office hour in a minute from now once everybody's out.
Thank you, Professor.
Thank you.